Good afternoon, lovely humans. Today we have our last section of classwork for the year. We're going to be doing section 931. So in the last two sections of chapter 9, we talked about solving one variable inequalities. So finding the boundary point, right, setting the two sides equal, and then testing a point to see which, if it were greater than or less than. So today we're going to get into two variable inequalities, so when there's an x and a y, and think about what it means to be the solution when there are two variables. So for 965, we are going to remind ourselves what it means to be the solution to a two-variable equation. That way we can relate what we already know to inequalities. So take a look at 965. I'll be right back to go over it. So for 965, part A, we want to test the point -1, 5. We're really relating in this problem the equation and the graph. So a point that's on your line means that it makes the equation true. So when I plug in -1, 5 to the equation, y equals -2x plus 3, I get 5 equals 5, which is a true statement, which is why it shows up on my line. Because this line is representing all of the solutions, xy pairs that make this equation true. We can do the same with 2, -1, and see that it also makes the equation true, therefore it's also on the line. But when we plug in a point like 0, 0 that's not on the line, we get this very false statement that 0 is the same as 3, which is why we're not on the line. So for part C, a point on the line basically must have an x and y value that together make the equation true. Awesome. Try 9-66 part A, please. In the video, I'm giving you the points that I'd like you to try. And if they make the point, or if they make your inequality, y is greater than or equal to -2x plus 3, true, then you're going to plot them on the graph. Otherwise, you can mark them false. All right, so to test a point, what you need to do is plug in your x and y value. Remember that the y value is second. Into the inequality, and you want to see if it makes a true statement. So in this first case, we had 1 is greater than or equal to -2 times 1 plus 3. So that simplifies to 1 is greater than or equal to 1, which is a true statement, right? If it's equal or greater than, then it's true. So 1 equals 1, we have a true statement. So I plotted it over here, 1, 1. I didn't do the work for the rest. I trust you to do that. And I'll be looking for that. But if you have, once you plot them all, you'll notice that there is kind of a trend. All right, so here are our not solutions, and then here are our solutions. So what we're about to discover is super important. What I'd like you to think about is, in part B, there's a bunch of questions for you to think about, and they're really important. So give it your best shot, see if you can come up with any patterns and any conclusions, and then we'll go over it. All right, so the first question that we wanted to think about was, are there any points that we think are solutions to this inequality, but we didn't plot? And so what I would argue, let's take a look at what our inequality says. It says that the y value, right, so the vertical part, is bigger than or equal to -2x plus 3. So we know that this purple represents where it's equal. So what we're really trying to figure out is, what are the points that are vertically above our line? So if we go to a point on our line and think about what's above it, any point should work. This point, this point, this point, this point. And if we really wanted to, we could fill in all the dots that we could possibly think of, but that would take super long. So what we do is we shade. And some people get really fancy about this. I like to just kind of draw a grid like that, just to show, or some people like using highlighters, that everything that is above our line is actually a solution. Everything that is greater than or equal to where we know these two things to be equal, that's going to be where our solutions live. If you don't believe me, try another point for yourself. You can try 3, 3 or 5, 1 or any of those points, and they should all make your inequality true. Super cool, big moment. We just discovered what it means to be the solution to a two-variable inequality. So the second question that they ask is, do we think any of the points are misplaced? Well, you did them with me, so no, none of the points were misplaced. If we did it as a class, there's usually someone who got the inequality symbol the wrong way or something, and then there's a misplaced solution. And then the points on the line are solutions, or are they not? So they are solutions because remember that we have y is greater than or equal to negative 2x plus 3. So this line represents where y equals negative 2x plus 3, which does satisfy the inequality. How many solutions are there? Well, we could try to count them, but then we'd be here for literally ever. So, for literally ever. totally a thing. And so, we can't count them up. There's actually a whole, what we call a half plane of solutions. So, infinitely many solutions. How can we be sure that there aren't any solutions on this other side? Well, just like there was a boundary point in the inequalities we were looking at in one variable that was shaded or not shaded in, here we have a boundary line. So once again, this line, just like a boundary point, separates all of our solutions from all of our not solutions. It's the tipping point. Once we know where they're equal, we can say where they're bigger or smaller. And I think that's all the questions for part B. So let's look at 967. Right, so in 967 we get some more practice identifying inequalities. So the idea is we first want to look at what is our boundary line or our boundary curve. So in this case it's a line. And it is the same line as before, so y equals negative 2x plus 3. But this time we are shaded on the other side than what we were looking at before. So we must be looking at, since we're looking at all the values below negative 2x plus 3, we'll write y is less than or equal to negative 2x plus 3. Part B asks, what if we aren't or equal to, right? What if we had y is greater than negative 2x plus 3, or y is less than negative 2x plus 3. So in that case, similarly to how we wanted to use an open circle when we were looking at inequalities in one variable, right? So in one variable, if I had x is greater than 3, and this was 3, I'd use an open circle. So that helped to show that 3 was the boundary, but we didn't shade it in because 3 wasn't a solution. So in this case, what could we do? Well, the line is still really important, so we want to somehow still show that there's a line there. But what we're going to do is put in a dashed line. So if you ever forget, this is why we do work in pencil, because then you can just kind of erase it. So we are going to use a dashed line if the boundary isn't part of the solution. So for these cases. For our boundary. And that's similar to how we use the open circle when one variable. Okay, let's look at 968. If you feel comfortable going for it using this information, go for it. If not, definitely watch the next segment. I'll be going over 968A and a good step-by-step process you can use to graph an inequality. So up here I've put kind of a step-by-step process that you can use to graph an inequality. So step one, you want to figure out where your boundary is. Once you have your boundary, it separates all of your solutions from your not solutions. So we're going to graph that. In part A, I'll use as the example. Oh, this is 968. Oops. I'll go through the steps for part A. So we have a boundary that's going to be a dashed line. So because we're greater than this value, we don't want the boundary in the solution, so we'll use a dashed line to represent that. Our y-intercept is -1, and our slope is -1/3. So then we can put a dashed line here. There we go. Step 2, we want to choose a point that is not on the boundary line and test it. My favorite point to do this with is 0, 0, because it makes the x's go away. We don't have to deal with the 1/3. So if possible, try to test 0, 0. It's a great point. So original inequality, we have 0 is greater than -1/3 times 0 minus 1. So what we get is 0 is greater than, goodbye, -1. That's true. 0 is bigger than all negative numbers. So what does that mean? That means that we just found a solution. 0, 0 is a solution. And since we know that our boundary separates all of the solutions from all of the not solutions, that means that we just found where all of the solutions are. So we can shade above the line. Now usually, so if we have like y, so in this case it was y is greater than, right? And that's awesome. If we have it like that, then greater than just means above, and less than means below. Easy peasy. But sometimes, like in part D of this problem, if you're not in y equals mx plus b form, things get a little bit dicier. So I would like you to always test a point to decide which side to shade. Have at it for parts B, C, and D. I'll be back to go over them. Okay, last one. So we're going to do like a learning log entry to kind of put together everything we've learned today about two variable inequalities. So first, how do we graph them? So if it is like this or this without the or equal to, then that means we're going to use a dashed line. And then if it is or equal to, we'll use a solid line. How do we determine which side to shade? So we are going to test a point in the original inequality. And if it works, that means that we just found all of our solutions, right? Once we find one solution, we know that all of the solutions are on that side of the boundary. If it doesn't work, then we just found out where our solutions aren't. So it must be on the other side of the boundary. It doesn't really matter what points that you test, as long as they aren't on your line. So 0, 0, and 1, 1 are usually nice options if you can use them to test in your inequality, but you don't have to use those as long as they're not on the line. And you only need to test one point. So as I've said, your goal is to separate the solutions and the not solutions. So once you find a solution, you just found all of the solutions. And once you find a non-solution, you just found all of the non-solutions. That's the power of the boundary line. Because once you know where the boundary is, you just need to test a side to see which one has all the solutions and which one has all the not-solutions. So that's all for today. Thank you so much for watching. Remember that if you have been watching these, I would really love if you could email me, just being like, yup, been watching the videos. Because I feel like I'm teaching into a void and I miss you all, and that's all. So good luck on finals. I will see you next week if you have questions at our conferences.